Hello everyone, welcome back to this channel. In this video, we will be taking a look at an application of finite state machines, and we will be implementing it with the help of a GHDL and GTK wave. In our last video, we spoke about finite state machines, the different types of finite state machines, and how to encode different states within them. If you haven't watched that video, I would highly encourage you to do so. Before moving on to this practical example of how to implement a traffic light system using a finite state machine and VHDL, if you have found this channel useful, consider subscribing or joining the membership. You can even support the channel through Patreon, where you can find all the notes behind these videos, especially this VHDL playlist. Okay, so without further ado, let's take a look at the application we will be implementing using a finite state machine. When we are trying to represent a traffic light, we have discussed previously that there are three, in our previous video, and as you may know, that there are three main states. The traffic light can only be in a red light state, a yellow light state, and a green light state. And there's a specific sequence that follows. Now, if we wanted to implement and model that sequence of states, we would need to introduce two additional states or intermediary states. First, the transition from yellow to green state and the yellow to red state. To emulate real-life traffic light systems, we have added a counter to the finite state machine, where the change in state depends on the counter's value. The counter has a value from 0 to 100 and will remain in the red light state when the counter is at 10 to 50, so that's 40 counts approximately. Then it will transition to the yellow to green state and remain there for 10 more counts up until we are in the 60 counter mark. And then it will transition to the green light state when we are done with those 10 counts, and will remain there for another 39 counts, meaning when the counter reaches 99, it will transition from green to yellow to red, and then the counter will reset to 0, and it will remain, the state will remain in the yellow to red state for 10 counts before transitioning back to red, and so on and so forth. Jumping over to the code, to design the traffic light system that we talked about, we would need to first create the entity of that traffic light system. Our traffic light system has 3 outputs and 2 inputs, the clock and the reset as input, and the red, yellow, and green light as the output. Now that we've simply defined an entity, let's talk about the functionality of this traffic light system that is designed using the finite state machine. To use finite state machines, we would need to create a type for that finite state machine. That type will contain the different states that the traffic light system can be in or can lie in. Therefore, to do that, we would need to define the type over here in between the architecture and begin, where the type is either red, yellow to green, green, and yellow to red, as we've discussed. Then we would need to define a signal of the state, the signal state of the type traffic here, such that the state is a signal that can only lie within 4 possible states: red, yellow to green, green, yellow to red. And since our traffic light system transitions from one state to another according to a counter's value, we have also defined a counter signal over here that is of the type integer that ranges from 0 to 100. And I went ahead and initialized that counter to 0 and the state to red. Now, finite state machines are sequential statements. Therefore, we need to put them within a process. So we went ahead and defined a process here that has 2 signals in its sensitivity list, the clock and the reset. Let's take a look at the reset. What happens if the reset is high? In our design, when the reset is high, it means we need to reset the inputs and outputs. Therefore, the counter has been reset to 0, and the outputs over here have been also reset to 0, and the state has been set to red. Otherwise, if there is a rising edge in the clock, then the counter would increment by 1. So every rising edge, we would see the counter incrementing. Okay, now here is where the finite state machine starts to begin. So to design the finite state machines, we use case when statements, where we observe the case of the state, and when the state is at a certain value, certain things happen. So when the state is at the red state, the red light should be turned on, and the yellow and green light should be off. If the counter has reached 50, as we've seen from the finite state machine diagram in the slide, then we should set the red light to 0. And when it's equal to 50, that's when the transition happens from the red state to the yellow to green state. Let's look at the second state. When the traffic light system is in the yellow to green state, that's when we turn on the yellow light and set all the other lights to 0. And if the counter reaches 60, that's when the yellow light is equal to 0 and the state transitions to green. Now, when the state reaches green, what happens? The green light should also be turned on and the others should be off. And if the counter reaches 99, and this is of course based on the design we saw on the slide, then we would need to turn off the green light and indicate to our finite state machine that it would need to jump over to the next state, which is yellow-red. And since we've reached the maximum of our counter, we would need to reset the counter. Then, when we are in the yellow to red state, we would need to turn on the yellow light and turn off the red and green light. And if the counter is equal to 10, we would need to turn off the yellow light and indicate to the finite state machine that it needs to transition back to the red state. And so this is how we can design a simple finite state machine for a traffic light system using the case when statements. To test this out, I've designed a simple test bench, as you can see, where we've only controlled the two inputs, the clock and the reset. And using GHDL and GTK wave, I've created a VCD dump file with the results of the timing results of this test bench. So let's go ahead and open up GTK wave and the result to observe what happens, or what is the output of this code that we've written, or this finite state machine. So we have the clock, and within the clock, or let's say within the finite state machine, I've defined the clock frequency to be as follows, such that the clock period has a period of 1 milliseconds. And so we need to zoom out such that we're in the millisecond scale. Okay. And then we have the reset. This is where the reset is transitioning to low. And then we have the outputs of the entity, the red light, the yellow light, and the green light. When the reset is high, as expected, we have 0 outputs in the red light. No red light is emitting, no yellow light is emitting, and no green light is emitting. However, when the reset is off and the clock has reached the rising edge, we can see the red light being on. And we expect this to be on for about 50 milliseconds. So when we zoom out, we can see that yes, in about the 51 millisecond mark, we can see that the red light has transitioned from on to off, and then we have the yellow light being on for about another 10 seconds. And then after that, it turns off, and the green light is turned on for about until 99, until when the counter reaches 99, which is at the 100 millisecond mark, and then it turns off. We can then see the yellow light turn on for another 10 seconds, and then the red light turn on for another 40 seconds, and so